one of the things that the chain rule gives us is the tools we need to find the derivatives of all kinds of logs and exponentials, not just e-based logs and exponentials. So my goal for you today is I can find the derivatives of non-base e-logs and exponentials. So here's the derivative formula for logs of any base. I want you to, as you're looking at this formula and you're remembering this, I want you to really emphasize to yourself that natural log of a is a number. And in this formula, I want you to know that this would work if we were trying to take the derivative of common log of x. The derivative of common log would be f prime of x would be 1 over x times natural log of 10, because the common log has an invisible base 10 here. But would also work if we were trying to take the derivative of log base 3. But also just remember that natural log of a is a number. All right, so I'm going to walk through the proof of this derivative, because if you understand where it comes from, you're more likely to remember it. And you could always derive it again if you want to. This one is actually pretty straightforward. The first thing you do is you do change of base so that you can rewrite it as a natural log, because we know how to take the derivative of natural log of x. And that is a pre-calculus concept, change of base. So if you need to Google change of base, that's where that came from. And then we remember that natural log of a is a number, so we factor that out in front. So we have a constant times the natural log of x. And then when we do the derivative, we can use the constant multiple rule, because natural log of a is a number, 1 over natural log of a is a number, and so we just take the derivative of natural log of x and multiply by that. And that's where this comes from. So it's really pretty straightforward of a proof, as long as you remember the change of base formula. And remember to treat natural log of a like a number. So here's an example. I would recommend that you pause the video here, give this a try, and then I'll walk through it. So pause now and try it. So I started by finding the y coordinate. I plugged 8 into that f of x equation to get the y coordinate. Remember that log is really just looking for the exponent. So whenever you see a log, think to yourself, what's the exponent? So what's the exponent of 2? That gives you 8, so that means that f of 8 is 3. We're using that new derivative formula to find the slope, so we took the derivative, and then we plug 8 into that formula. If you don't have a calculator, the first answer is totally okay, 1 over 8 natural log of 2 as the slope. If you have a calculator, make sure you're reporting your answer correct to 3 places to the right of the decimal. So here's a picture of that graph. The slope is, as you can see, not very steep, and we are passing through the point 8, 3. All right. The other new derivative in this section is the derivative of any exponential. So in this case, a is a number, and again, treat natural log of a like a number as well. So this is how we could take the derivative of, if we have f of x equals 2 to the x, this is how we could take that derivative, and we could say that would be 2 to the x times natural log of 2. And this is a proof of it. This proof is a little more involved than the last one and does actually require the chain rule, but it's not something that's beyond you to understand. So I'm going to walk through it so that you can understand it. The first thing is that we're going to natural log both sides. So we're allowed to do that. It's an equation. We can take the natural log of both sides. And then the next thing we're going to do is we're going to use the exponent property of logs to bring that x down in front. So we use the power rule for logs, which brought the x down from the exponent, and that's one of the properties of logs. Now that we have that, we're going to get rid of the natural log that we did by exponentiating both sides. So we're going to get back to a y equals equation after this step. So when we simplify e to the natural log of y, we get just y. And now we're ready to take a derivative. We did all of that algebra. We haven't taken a derivative yet, but this is the derivative of e to the x with the chain rule. And I want you to remember that natural log of a is a constant, so you're really taking the derivative of e to the x, which is e to the x, times the derivative of the baby, which is some number times x. So that's going to be natural log of a. And then we can do a little substitution. We noticed in this step that y is equal to e to the x natural log of a. So we can rewrite this as y prime is equal to y times natural log of a. And then there's another substitution we can make. Because y is equal to a to the x, we can substitute a to the x in for y. And the reason we want to do that is so that our answer is all in terms of x, because that's how our question was. And we got to the derivative that way. So if you're comfortable with log rules, I don't think this is a bad proof. And if you are always constantly reminding yourself that natural log of a is a constant. No pun intended. All right, so here's an example problem for this derivative property. So we're going to write the equation for the tangent line to this function at x equals -2. And I will encourage you to pause and give it a try, and then unpause and watch my solution. So first I found the y-coordinate by plugging in x equals -2, and I got that the y-coordinate was 81. And then I found the slope by taking the derivative, remembering that 3 to the x squared is a composite function, so I needed to take the derivative of x squared at the end there. And also remembering that natural log of 3 is a number. If I didn't have a calculator, the first answer would be totally fine. It's okay to have an answer with a natural log in it. But with a calculator, I can see how incredibly steep this line is. It has a slope of -355.950. And so that's kind of an interesting aspect of exponentials. They just grow so fast. All right. That is the lesson for today. So this is a pretty light day for calculus. Those are two derivatives that you do need to know either how to derive them so you can always have them, or you need to have them memorized. All right, thanks so much. Bye.